Hello everyone. In this video, we are going to look at vibrations of multi-degree of freedom systems. So any system that has more than one DOF, and we're going to focus on free vibrations. But the system can or cannot have damping. So first we start with systems with no damping, and then we're going to end up with systems that have damping. Our pictures and equations are coming from Theory of Vibrations with Applications by William Thomson et al. Everything comes except for the last part, the one that has damping. That is not in the book of Thomson. That I had to add myself. So in Thomson, if you look at the vibrations, they're for multi-DOF systems, they're all done without any damping. So here we're going to look at systems with two DOFs, but this approach can be extended to any higher degrees of freedom. So the goal is to find the natural frequencies and mode shapes of a system with several degrees of freedom. And we can see that it is going to turn out, if there is no damping, it is going to be a simple eigenvalue, eigenvector problem. How? So here, consider this mass spring system, masses M1 and M2, spring K1, K2, K3. There is no friction below the tires, rolling without slipping. We draw the FBDs of the two objects, and we only include the forces along the X direction. Remember, each one has mg and n, but we really do not need to care about them because all we care about is motion in the X direction. So these mg's and these n's will have no effect in the X direction. So these are your two FBDs. So here, because X1 moves to the right, this spring is going to be stretched. So it is going to apply a force back to the left, which is K1 times X1. If assuming that X1 is bigger than X2, by the way, this assumption has no effect on these terms. It's just to make life easier. Otherwise, you can assume that X2 is bigger than X1. You're going to get the exact same term. So if X1 is bigger than X2, then this side is pressing further than this side is pulling. Therefore, the spring is going to be compressed. And so on this side, it is going to push back at X1. And the force of it is going to be K2 times the difference between the two displacements. So it's going to be K2 times X1 minus X2. And the reaction of this force is going to be applied to mass M2, and on the other side, X2 is compressing the K3, so K3 is going to push back at it by K3 times X2. That's all it is, okay? So these are your FBDs. Now remember, I said this assumption does not make any difference. Let me just show you that. So you might say, well, who said so X1 is bigger than X2? What if X2 is bigger than X1? Let's see what happens if X2 is bigger than X1. Would we get any different force for these two forces in the middle or not? The answer is no, we won't. Let's see why. So if X2 is bigger than X1, then this side is going to move more than the left side. So this side is pulling the spring. This side is not pushing enough, so the string is going to be stretched on this side, so it should push back. So the force is going to be this way because this side is pulling more, and the value of it is going to be the spring constant times the difference between X2 and X1, which is X2 minus X1. Remember, X2 here is bigger than X1. Now look at this one and look at this one. Look at these two forces. Are they the same or not? They are. All you need is to, because you see the only difference between them is a negative sign, but also the directions are opposite. Well, if you reverse the direction or you put a negative, that has the same effect. So you can see that these two forces in different directions with the negative sign is like 2 times negative applied, and these are the same force. So it doesn't matter really whether you use X1 bigger than X2 or X2 bigger than X1. Just pick one and move on and get your forces, okay? The result is not going to change. So here I got my FBDs. Now I'm going to write the equations of motion. For this object here, the M1, this force is in the negative direction. This force is also in the negative direction. So if you write it, the equation is going to be M1 X1 double dot equals negative K1 X1 negative K2 times X1 minus X2. Now, if you bring these two negative x1 terms to this side and combine them, it's going to be x1 times k1 plus k2, which is this guy. And this positive force of, you see here, when you multiply k2 and x2, these two negatives would cancel, they become positive. But if you bring it to the left side, it becomes negative. And then equals 0. So this is that's your first ODE that you have up here. Then if you write it for M2, you're going to get M2 x2 double dot equals what? Equals negative K3 x2 and then positive K2 times x1 minus x2. Again, if you bring these two negative x2 terms to this side and factor out x2, it's going to become positive x2 times k2 plus k3, which is this guy. And this negative term here, which is, this positive term, which is k2 times x1, if you bring it to this side, becomes negative k2 times x1, which is this one here. Again, equals 0. So you see, these are the two governing ODEs. Now, one thing you can do is you can write these two equations into a matrix format. So you can write it as this matrix times the x double dots plus this matrix times the x's equals right-hand side of 0. And if you write it this way, and you call this combination x1 and x2, you call it vector x. So this is going to be vector x double dot. Then this matrix here, we can call it the mass matrix, and this matrix here is called it the stiffness matrix. So it becomes m x double dot. Again, this x double dot here is a vector, and this x is a vector, and this 0 is a vector, two zeros. So you can write your equation, governing equation, into the matrix format. Now, one thing I want you to pay attention that the mass matrix and the stiffness matrix are both symmetric. Pay attention to this part. This is an important property of M and K matrices. Look at that. They are symmetric matrices. Okay, the off diagonals are the same. Okay, or the transpose of them is the same as themselves. So this is an important property that when you extract the equations of motion in matrix format, the mass and the stiffness matrices are symmetric. If you get something that is not symmetric, you definitely have done something wrong. Okay, you definitely made a mistake. So go back and fix it. Okay, so this so far is the equation of motion. Before we talk about the solution of it and natural frequencies and mode shapes and something, I want to give you another nice hint about these equations. So if I want to look at these M and K matrices, look at the components that are inside them. So the M matrix is a diagonal matrix, and the diagonals are the masses of the objects. Okay, that's not hard to see. Now about K, look at the K. The diagonal elements are going to be what? The diagonal elements is going to be some of the springs, some of the spring constant that are attached to that math. If you look at M1, which springs are attached to it? K1 and K2. And since they are on each side of it, they act like parallel springs, so you can add them together. Similarly, for M2, what springs are attached to it? K2 and K3. So you see K2 and K3 are on this diagonal. Good? Yes? So you see how to find the diagonals. The diagonal is some of the spring constants of the springs attached to it. Good? Now, what about the off diagonal? How would you find this? This one that is relating x2 to x1 equation and relating x1 to x2 equation, because it is the linking between x1 and x2, it should be the spring constant that is between x1 and x2. It's the one that connects motions of x1 and x2 together, and guess what? That is K2. Now, for both of them, it is going to be negative. Okay, so the spring constant of the one that is between the two, it is going to be what? It is going to be negative. Okay, that's how you form the M and K matrix. For instance, if I want to extend this system, let me extend this system. So here I go ahead and extend it to 3DOF. Okay, I just want to show you how to get M and K without even finding the differential equations. So here I call it M1, M2, M3, and then here K1, K2, K3, and K4, right? So if I say what is the M matrix here and what is the K matrix here, what would you say? Look, M is going to be diagonal, so it's going to be M1, M2, and M3, and the rest of it is going to be 0. K is going to be what? Well, for this one is going to be the K's that are connected to M1, so that is going to be K1 plus K2. For this one is the K's connected to M2, so that's K2 plus K3. And for this one, the K is connected to M3, so K3 plus K4. Now, what goes here? This is the 1, 2 element, so it is the connection between 1 and 2. What is it? It's K2, but it should be negative K2. What is this here? This is the one that is connecting motions 1 and 3, okay? Because that is what? That is the connection between 1 and 3. Is motion 1 and 3 connected at all directly? No. M2 is in between, so this guy should be 0. M3 motion should have no effect on M1. Similarly, since it's symmetric, this is going to be negative K2. I don't even need to fill it. This is going to be 0. The only thing I need to find is this one, 2, 3. Are 2 and 3 related? Yes, through K3. So this is going to be negative K3. And again, since it's symmetric, this is going to be negative K3. Done. Okay, you see how I can easily find M and K matrix just by looking at the system. And once I have M and K, I'll show you I can easily find natural frequencies and the mode shapes. And you don't even need to for the differential equation. So fine, my equation is of this form. Now, how do I find the motion of the system? What are the frequencies of the system and so on? So since this is a linear ODE and the coefficients are all constant, the solution has to be a exponential and with some amplitude x and with some exponential with frequency omega, or you might call it omega n, okay, because that's free vibration. If I plug in this solution here, x double dot is going to be negative omega squared times x. This whole thing is actually going to be multiplied by e to the I omega t, or omega nt. So this x double dot is going to be negative omega n squared times magnitude x times exponential of I omega nt. But you have to multiply it by m. And then this x is the same thing, except k will be multiplied by x. So if you factor out this exponential and set it to 0, this exponential can never be 0. So the coefficient of this exponential, which is this guy, should be 0. So that matrix should be equal to 0. Okay? Now, what I have here is k inverse minus omega squared mx equals 0, or if you want, you can take the negative term to the other side. You will get k times x equals omega squared m times x. Okay? Now here, you're going to call this omega squared lambda if you don't mind. This is just a scalar. And you multiply both sides of this relation by m inverse. Multiply both sides of it by m inverse. Since this is a scalar, m inverse and m would cancel. You get I times x is just going to be x. And here on the left side, you have m inverse k. So you will get m inverse k times x. is going to be lambda times x. Now this is a matrix. If you give this guy a name, call it A matrix. Now look at the problem you have. A times x is lambda times x. Yeah, what kind of problem is that? You're right, that's an eigenvalue problem. So you see, if I form the M inverse K matrix, then lambdas are the eigenvalues of this matrix, and the amplitudes of the oscillations x are going to be the eigenvectors of the A matrix. Now lambdas are what? The eigenvalues of A. These are omega squared. So if I want the natural frequencies, what should I do? I should find the eigenvalues of A, and then, because these are omega squared, I have to take a square root of them. Right? So omega n's are going to be the square root of eigenvalues of A. Once I find those eigenvalues, take a square root of them, it gives me all of the natural frequencies. Now this system has two DOFs, so it's going to have two eigenvalues and it's going to have two natural frequencies. And similarly, these x vectors, which are 2 by 1, are going to get two eigenvectors. Each one of the eigenvectors correspond to one of the eigenvalues. So I get two eigenvectors and two eigenvalues. Now again, the square root of the eigenvalues will be the natural frequency of my system. And then those eigenvectors is what we call a mode shape. Why do we call it a mode shape? I'm going to explain in this numerical example that is coming. Okay, but I'm just trying to explain to you how you will get natural frequencies and mode shapes of the system. So to make it more tangible, here we are going to look at this system, but to make life simpler, we are going to not use M1, M2, K1, K2, K3. We assume all the springs are the same K and both of the masses are the same M. So we still solve it parametrically, but we make it a little bit simpler. We reduce the number of parameters. So if we do so, what would we get for natural frequencies? What we get for these x's or mode shapes? What's the meaning of these mode shapes? And where are the nodes? So here I want to explain a bunch of things for you. So be ready. So first thing we do is we want to go ahead and calculate the natural frequencies or the eigenvalues and eigenvectors. So the first thing is we need to form the A matrix, and remember A matrix is M inverse K. So the first thing we need to do is to form M and K, then find M inverse times K, and then find the eigenvalues and eigenvectors of it. And this is my M, this is my K. So let's go ahead and do that. So in this system, M is simply going to be M00M because M's are the same. What about K? K, remember it was K1 plus K2, so it's going to be 2K minus K2, so minus K, and again 2K. So this is what? This is M and K. Now we go for A. What is A? A is M inverse times K. Now the inverse of a diagonal is going to be a diagonal where these elements are going to be reciprocals of these. So it is going to be 1 over M, 0, 0, 1 over M, and then this guy here. 2K, negative K, 2K. So let's simplify this. So you're going to get basically 2K over M. You're going to get negative K over M. You should get negative K over M, and again 2K over M. So that's the A matrix. Now I need to find the eigenvalues and eigenvectors of this. If you remember from math, the way to find eigenvalues and eigenvectors is first you go for eigenvalues by solving a determinant equation, and then from there you can go for eigenvectors. So let's go ahead and do that. The way we find the eigenvalues is we set the determinant of A minus lambda I, and this I is the identity matrix with the same dimension as A. Since A is 2, this identity is 2 by 2. This, you set it equal to 0. If you don't know this, please go and watch my videos on eigenvalues. And I have 2 videos on eigenvalues under my playlist, Engineering Mathematics. And over there, actually, I explained that eigenvalues are used for vibrations. When I talked about applications of eigenvalues, I actually mentioned this problem or problems similar to this. So what do you get? So here you bring this matrix, and on the diagonals, you subtract a lambda. And then the determinant of this, you set it equal to 0. Well, what's the determinant of this? So it's going to be the diagonals minus the off diagonals. So it is going to be 2k over m minus lambda, the whole thing squared, minus these 2 squared. So it's going to be minus k squared over m squared. So let's simplify this. So you're going to get 4k squared over m squared plus lambda squared, and then plus 4k lambda over m, or minus that, sorry, minus k squared over m squared. This whole thing is 0. So this should be a negative. Now these 2 would cancel each other, so you only would get 3 of that. And now, if you look at it, it's clearly a quadratic equation. This is your power 2, this is your power 1 term, and this is your constant. Okay? And if you want, you can multiply the whole thing by m squared, or you can just leave it as is. So if you solve for the 2 roots, lambda 1 and 2, they are going to be negative b, which is negative of this linear term. So it's going to be 4k over m. And then plus and minus b squared, which is again this 4k over m, the whole thing squared, minus 4 times a times c. A here is 1, c is that 3, so 4 times 3 is 12. K squared over m squared. And then the whole thing divided by 2a, which in this case is simply 2. So now what do we get here? Here is 4k squared, so you get 16k minus 12k, you get 4k. So here you get 4k over 4k squared over m squared. You apply the square root, you get 2k over m. So what you will get is 4k over m plus minus 2k over m divided by 2. And if you simplify, your values are going to be 6k over m and 2k over m. Okay, so these are your lambdas, but remember, lambdas are the square of the natural frequencies. Okay, so this guy is omega number 1 squared, or omega n number 1 squared. This is omega natural frequency number 2 squared. Okay, so if you take a square root of and actually I made a small mistake here. I didn't divide by 2. So one of them is 3k over m, one of them is k over m. Okay, therefore if you find your natural frequencies, omega n number 1 is going to be square root k over m, and omega n number 2 is going to be basically square root of 3k over m. So these are the natural frequencies of this system. Now, you might say, what are these? Well, these are the same thing except when you use 2m for m. So m1 if you used m, and m2 if you use 2m, and do the calculations, this guy becomes a 2. Therefore, here there is a 2, and that will change everything. So if you just make that mass 2 times bigger, these are the things that you will get. And why did I copy them here? Because I want to explain something to you. But if both masses are the same, these are the frequencies that you will get. If the one mass is heavier than the other, these are the frequencies that you will get. And you know, square root of 3 is about 1.72, right? Or actually 7.3. So what do you see here? Let's take a look. If I made one of the masses, so here again, these two masses are the same with all these k's. Here, one is m, the other one is 2m. So which system has bigger frequencies? Clearly you see that this system with 2 m's has bigger frequencies. Look, this is 3, here is 2.36, this is 1, here this is 0.63. So clearly this system has a bigger frequency. Why? Because this one has a bigger mass. And you know, mass is in the denominator of frequencies, so bigger mass means smaller frequencies. And you can see that, of course, okay? So adding more mass means bringing down the frequency. Now, one thing I want you to pay attention, and that is very critical, is remember that these two frequencies belong to both of the objects, belong to the whole system. It's not like omega n1 belongs to object 1, omega n2 belongs to object or mass 2. No. Both of these objects, the whole system, has two frequencies in it. So as you'll see in a second, if I look at the response of each one of them, x1 or x2, in both x1 and x2, there are two harmonics. One of them is with this frequency, so like a times square root 3k over m times t. Okay, sine of that, I'm sorry. Sine of that is a harmonic. And the other one is, for instance, b times cosine of that, or you can add a phase if you want. So let me add a phase to make life easier. So add a phase. And then what? This is the first harmonic in it, and then the second harmonic is going to be something like this. Do you see? So there are two harmonics in them. Two harmonics. There is not one harmonic in the response of this system. Both of these frequencies, they appear not only in x1, but also in x2. So x2 is going to be like c times sine of the exact same thing. And then d times sine of the exact other frequency. And this 4 constant will come from 4 initial conditions. So do you see that? Both frequencies exist for the whole system, and of course this one has bigger masses, so it has smaller frequencies, both smaller frequencies. Okay, so this is about what? This is about the natural frequencies or the harmonics that are available in the response of the system. This is natural frequency. What about the mode shape? For mode shape, we have to find the eigenvalues of this A matrix. So now we have to go back to this matrix with those lambdas that we found. And remember, these are my lambdas. This is lambda number 1. This is lambda number 2. With those two lambdas, I have to go back to this equation that A times x, magnitude x, equals lambda times x. And since now I have lambda for a1, I can find x1, and then for lambda 1, I can find x1, and then for lambda 2, I can find x2. 2, these mode shapes, these vectors here, which here is shown by phi of x or capital X, doesn't matter, it's just a notation. So let's go ahead and look at this matrix, this M inverse K, and see if we can find the mode shapes of this one. So again, remember A times X equals lambda times X, or if you want, you can bring both of them to one side and set it to 0, so you can write it like this if you want. And X, remember, is a matrix, or if you want, you can write it as A minus lambda I, the whole thing, times X equals 0. That's another way you can write it. Now, this A minus lambda I, if you remember, it is going back to A. Look at A, 2k over m and negative k over m. So it is going to be 2k over m minus lambda 1 negative k over m, negative k over m, and again 2k over m minus lambda 1. So first I plug in lambda 1 in it, and I'm looking for x1. Now x1 is a 2 by 1 vector, so I can put two numbers in it, whatever you want, a and b, or you might call it x11 and x12. So this is equal to 0, 0. Now I need to replace lambda 1 here. Lambda 1 was, if you go back and look at lambda 1 is k over m. So I have to come back here and replace it by k over m. Well, if I do that, this whole thing will be k over m. So if I multiply and expand, I get two equations. The first one is k over m x11 minus k over m x12 equals 0. The second one is going to be negative k over m x11 positive k over m x12 is 0. And if you look at these equations, they are the same equation. Both of them are the same equation. So you don't really have two independent equations. You really have one single equation. Why? Because initially you set the determinant of this guy to 0. Therefore, your equations are not going to be independent. They're going to be dependent equations. So you really can pick one of them, whichever one that you want. Doesn't matter. Let's say we pick the top one because they are the same. And you can get rid of k over m. And if you, from here, you see the result of either one is going to be that x11 equals x12. Okay, so when you're looking at the eigenvectors, you're not going to get definite number for each one of them. You're just going to get a relation between them because they are dependent in this case. If there are three numbers, still between the three of them, you find two equations. You cannot uniquely determine each one of them. And because eigenvectors are about a direction, we don't care about their exact magnitude, we care about the direction. For instance, one of the things that you commonly do is called normalization, okay? Or you can go with the magnitude of 1 for one of them and determine the other one. So if I pick this to be 1, what is the other one? This guy is also going to be 1. So you see, if both of them are 1, my first mode shape, x1, is just going to be 1 and 1. Or if you want to get a magnitude 1 for it, you can divide both of them by square root 2. But all I need is a direction. This direction is this direction 1 and 1, correct? 1 in this direction, 1 in this direction. Okay? If it's in 2D, you look at it in 2D. Now, it's a separate thing in here. 1 and 1 means what? I'll draw it and I'll show you. But that's my first mode shape is 1 and 1. Okay? That's the first mode shape. Now, let's go ahead and do the second mode shape. See what kind of vector we get for the second mode shape. So now I go back to the second mode shape and I'm gonna get lambda 2 if you don't mind. Let me clean it up. So this here, I put it up there. That corresponds to omega n1 or lambda 1. That was square root k over m. Now for omega n2, which is square root 3 km, or lambda 2, which is 3 km, I want to find vector x2. So here for that lambda 2 now, and these guys I call them x21 and x22, I have to plug in lambda 2, which is this guy under the square root. So I plug in 3k over m. So this term is just going to be negative k over m. The same with this one. And again, if I expand it, you'll see I get two equations, but again, the equations are the same. So it's negative k over m x21, negative k over m x22 is 0. And the second one is exactly copy-paste. So again, I can pick one of them, not two. Any of them that I pick, and I get rid of this k over m's, I see that x21 is negative x22. That's what I find. Again, since I cannot uniquely determine them, for one of them I pick a 1 and I get the other one. So you see the other one is going to be 1 and negative 1. So these are my two mode shapes, 1 and 1, 1 and negative 1, and these are my natural frequencies. So these two are my mode shapes. These two are my natural frequencies. Now, what's the meaning of the mode shapes? So I learned about the meaning of natural frequencies. Natural frequencies are the frequencies of the harmonics using which the system is vibrating. Now, what about the mode shapes? What does mode shape mean? So this is the meaning of mode shape. Mode shape says, hey, if the system only vibrates in the first mode, so if somehow I assume that B and D are both 0, and the system only vibrates in mode 1, so the only frequency exists in the solution of that is only frequency number 1, then the ratio between this A and C is exactly this ratio, 1 and 1. So if this guy is A, this C should also be equal to what? Equal to A. Okay, whatever they are. And what is the A in this case? You'll find it from x1 of 0 and x2 of 0. Okay? And I'll show you again. We're going to go through that. So the ratio between them is 1 to 1. Now, what does that mean physically? It means if the system has to oscillate, let me go up a little bit so I can show you. If the system has to oscillate with only frequency omega n1, how does each object move? If this guy moves for so many units, this guy will move the exact same thing. The ratio of motion is 1 to 1. So many people draw it like this. They say this is 1, and this is the first mode shape. So this is 1 and 1. So they both basically move the same amount, okay? And what do we call that? Well, if they move the same amount, so x1 equals x2, this spring in the middle will not even be stretched or compressed. So both of them will act like a single object, okay? Because they are moving the same amount unless their initial conditions are different. Okay, if the initial condition of x1 and x2 are different, then of course their motion is going to be different. But if they are the same, then the ratio between them in that first frequency is going to be the same. Now, on the other hand, if I go ahead and look at the second mode shape, the second mode shape was 1 and negative 1. What does this mean? It means that if the system only oscillates in the second mode shape, in the second frequency, so basically these guys are 0, forget about those for a second. I only have B and D. The relation between B and D is 1 and negative 1. So if this is kind of like B, this could be like negative B. What does that mean? It means that if this guy moves to the forward, this guy moves similarly with the same amount backward, okay? So in this case, this one goes 1, this other side goes negative 1, okay? Well, what does that mean? If this is 1, this is -1. If you connect these two ends together, there is a point between the two that the displacement for it is going to be 0. Any point in a physical system where it physically does not move, that point is called a node. So nodes are the points in the mode shapes for which the displacement is 0, okay? And physically here, it means the points in between these two, when both they are coming at each other, this point here in the middle will not move. You are forming a node here. Now, this node shows itself more when you look at the vibrations of continuous systems like strings and so on, which I have videos for that under the same playlist, vibrations. And you see, I explained these nodes a little bit better over there because you can physically see the nodes. Here, I mean, like it's just a point on the spring. You cannot see it better. But if it was a continuous mass system, you can see that point a lot better. So anyways, this is the natural frequency and the mode shapes of the system, the meaning of each mode shape, and the location of the nodes, okay? This is the first part that I wanted you to learn. Now, if one of the masses was 2m, then the mode shapes will be different. Look here. So for the first frequency, the mode shape was this guy would go 1, this guy would go 0.7. So this is the mode shape. For the second mode shape, this guy goes 1, this guy goes -2.7. Again, if you connect these two together, you'll see there is a point here somewhere between the two masses which will not move. That's a node. Where is it? You can find it by similar triangles. So if the whole distance between them is L, you see this L should be divided by a ratio of 27.1 to 1. Okay, so if this whole thing is L, this is going to be like 2.73 over 7.73 L, and this ratio is going to be 1 over 7.73 L, if again this whole thing is L. Okay, so you can find the location of the node as well with similar triangles. Okay, so now for the very same system, we want to look at solution. Remember I said in the solution there will be two harmonics, correct? This part here. I want to explain this part for you. So now that I have found the frequencies and the mode shapes, I want to know if for the same system where both masses are m, all spring constants are k, if I give it some initial condition, what kind of solution would I get? And what is the effect of this initial condition? So what are the initial conditions? Remember, you have 2 second order ODEs, correct? If you look at your governing equation, there are 2 second order ODEs, so you need 4 initial conditions. 2 for x's, 2 for x dots. And this is exactly what I have provided here for you. So both masses start from rest, and the initial condition is 2 meters for x1, 4 meters for x2, and then I let the system oscillate. What's going to happen? Well, let's take a look. So remember, I said the solution is what? The solution is x1 equals a times sine of omega 1 times t plus 5. And then before I even write the second term, if I want to continue with x2, x2 will be something times the same frequency and the same phase. The first question is, what is this coefficient here? Do I just call it random b, or there is a relation between this magnitude and a? Because this is the first harmonic, the first natural frequency. So the weight between these two comes from the first mode shape. And what was the first mode shape? If you remember, the first mode shape was 1 and 1, right? So let me just find it here. The first mode shape for that frequency was 1 and 1. So what does that mean? If you go back and look at here, you see the mode shape will determine the weights for, because x is x1 and x2, correct? This is x. So the components in x, 1 and 1, will give the relative weight for x1 and x2 in that harmonic. So if this guy is 1, this guy is going to be 1. If this is a, this is going to be 1 times a, because the ratio is 1 to 1. Now when I go to the second part of the solution, the second harmonic, if I call that coefficient b, and it is sine of the second harmonic, which is this one, plus another angle, let's call it psi. What coefficient do I use here with the same frequency? Again, remember the second mode shape was 1 and negative 1. So if this guy is 1b, this guy should be what? Negative 1b. Okay, do you see the mode shapes? Where the mode shapes are used? Here. These are the relative weights of the coefficients, or the weights of the harmonics. These are those mode shapes. Now, how many unknowns do you have in here? You have A to find, you have B to find, you have phi to find, and psi. You have 4 unknowns, but guess what? You have 4 equations. So ideally, solving for these 4 unknowns should not be the hardest thing in the world. And for instance, if you plug in t of 0 in both of them, what would you get? So from these conditions that the values are 0 at the beginning, you know you will get 2 for x1. This is going to be a sine of phi plus b sine of psi. The second one is 4 equals a sine of phi minus b sine of psi. These are the first 2, and then the second equations, which are for velocity, here you have to take time derivatives out of them. So the time derivative of a sine, this frequency comes out, becomes a cosine, so you will get a times square root k over m cosine phi, and then plus b times square root of 3k over m cosine psi. And for the second one, again, you will get a times square root k over m cosine phi minus b times square root 3k over m cosine psi. You see, you got 4 equations and 4 unknowns, and I bet you should be able to solve for them, right? For instance, from the second 2, if you want to solve, if you just add them together simply, you'll see that this guy has to be 0, because if you add them, you get 2 times that will be 0. K over m square root cannot be 0. So what you will get from both of these is a times cosine of phi has to be 0. Okay, that's what you will get. Now, which one? Okay, that's the first thing that you will do. Now, if a cosine phi is 0 and you plug it back in these equations, clearly b cosine psi should also be 0. Okay? So a cosine phi and b cosine psi, they both should be 0. Now, what about these two? If you add them together, you see a sine phi has to be 3, correct? So from these two, if I solve, I get a sine phi has to be 3, And if I subtract them, I'll see that B sine psi should be -1. Let's make sure. Yes. Okay, so these are the 4 things that I will get. Now, what's the solution? Well, here, clearly, I can square this one and square this one and add them together. You get a squared equals 3 squared. So from these two, you clearly see a is 3. And if I square these two and add them together, you'll see that B has to be 1 or -1, correct? Because you will get B squared equals 1 squared. So B could be plus minus 1. Okay, now if that's the case, when A is 3 and A sine phi is 3, sine phi has to be 1, so phi has to be 90 degrees. And that matches this. And if you look at these two, if B is 1, since B cosine psi is 0, that also means psi has to be 90 degrees or 270 degrees. Okay, and then B times sine of phi is -1 here. If you want, you can take arctangent or arctangent 2 from these two, and you'll see the sine of it is -1, cosine is this, so psi is -pi/2, and B is going to be +1. Okay, so your solution is going to be, if you want to find the solution and write it all down, there we go. Remember, A is 3, so you get a 3 here. This one was also 3, so you get a 3 here. This guy was pi/2. And then B was 1, so you get only a 1 here. This B was -B, so you get a -1. And that angle, that last angle was -pi/2. So here you get -pi/2. There we go. You see here? Look. This is your solution here. Combination of 2 harmonics with the frequencies of square root k/m and square root 3k/m, and with the relative mode shapes of 1 to 1 and 1 to -1. All of these constants come from the initial conditions here. Okay? Now, one thing that I want to talk about is which one of these 2 frequencies have a bigger weight. I mean, look at the weights. This guy, this smaller frequency, has a weight of 3. The bigger frequency has a weight of 1. Okay? Yes? Which one has bigger weight? You say, well, of course, this first frequency has a bigger weight. Well, could we predict that from the initial condition? Well, kind of yes, because remember, your mode shapes are what? Your mode shapes are 1 to 1 and 1 and -1. This one is for the second frequency, this one is for the first frequency. Now, if you look at your initial conditions, the velocities are 0, but if you look at the positions, this one, this vector 2 and 4, is closer to which one of these? Well, of course, it's closer to 1, 1, not 1, -1. Because it's closer to 1, 1, guess what? It gets a bigger weight. Do you see that? What about this one? This one is quite a bit different than that, so it gets a smaller weight. So the closer the initial condition is to one of the mode shapes, that frequency will get a bigger weight in the solution. the further away it is from it, the further dissimilar it is from that mode shape, that frequency will get a what? Will get a smaller weight in a free vibration solution. Not only that, you can actually go one step further, and I explained that in a separate video on my channel under pre-release vibrations, the effect of initial conditions. I explained that. Actually, if you do a dot product between this vector and this vector, you kind of can get this guy. I mean, look at that. 2 plus 4 is 6, right? And 6 divided by 3 is 6 divided by 2 is what? 3, huh? Do a dot product between these two. 2 minus 4 is -1. If you divide it by 2, again similar to that one, you'll get this weight or this one. So if you want, please watch that video. Just the dot product between initial conditions and mode shapes can give you these weights of these solutions, okay? So mode shapes have lots of applications. There are lots of things that you can tell. They tell you how initial conditions will make which one of these frequencies to have bigger weight or more contribution, which one to have less contribution. Hopefully I made it clear for you. Okay, let me move on to my next example, which are two pendula, one with theta 1, one with theta 2, and they are linked by this spring K. If this spring was not there, each one will do its separate motion. You won't call it really a 2DOF system because they are not linked together. It's not a system, it's two separate systems. But because this spring is linking them together, now it's one system with 2DOF, and there will be vibrations now because there is some force that is restoring these positions back in addition to the mg. So what kind of thing would you get? Well, if you look at the FBDs, the FBD of each object will have the gravity force. There are, of course, forces of the pins, which will have no effect when we apply the moment about these fixed points. And there is a spring force. Now here, one thing we have to do is to make these vibrations linear, we assume both of these angles are small. Please watch my previous videos to see small angle assumption. If these angles are small, then the displacement of this point here, the point that the springs are attached, okay, this displacement here, how much is it? Well, this is simply going to be what? So this distance here is A. So if that's the case, and this is theta, this guy here is going to be A sine theta, or sin theta 1, but since angle is small, I can approximate it simply by A theta 1. And similarly, this one I can approximate by A theta 2. Now, depending on whether 2 is bigger than 1 or 1 bigger than 2, again, it's an assumption. You can pick any of them. Let's say here 2 is or 1 is bigger than 2. If 1 is bigger than 2, like this picture shows, then, and it seems like I reversed the order. Yeah, I reversed the order. Sorry about that. So this is theta 2. This is theta 1. So if theta 1 is bigger, then this side is pulling more than this side. So since this side is pulling, it is going to be pulled back. And since this side is falling behind, it is going to go this way. So that is the direction of those forces that you can see here. Look. And it is going to be the difference between these two displacements times the spring constant. So it's going to be K A theta 1 minus K A theta 2. And then the reaction of that force is going to, of course, be applied to this pendulum on the right. So it is going to be K A theta 2 minus A theta 1. Seems like there is a typo here. So this should also be Ka times theta 1 minus theta 2. Okay, they are action and reaction. They have to be the same. And here it says mgl theta 1. That's not really correct. That's just mg, m times g. Okay. And in this case, they are both m. So now you can take moments about these 2 points, O1 and O2. If you do that, remember from the pendulum vibration problems that we did in previous videos, only mg sine theta has a moment. The cosine one has nothing. So only this sine theta will have something. But remember, sine theta is the same as theta here because its angle is small. So this term will be multiplied by this distance L, and that is a negative moment. So if you take, let's say, sum of the moments about point O and counterclockwise positive, because the angle is counterclockwise, you will get what? You will get negative mg, and for theta, sine theta 1, I replace it by theta 1 times L. That's this moment. And then this spring force has a moment. What is the moment of that? Well, clearly, you see the moment of this is also clockwise, so it is going to be the force itself, which is Ka theta 1 minus 2, and then times the distance, and this distance here is also A. Or you can say it's A cosine theta 1, but since angle is a small, cosine theta 1 is simply 1, so it is approximated by A. So I multiply it by A. Now this is equal to I of this pendulum about 0.01 times theta 1 double dot. Good. And since it's a concentrated mass at distance L, I about 0.0 is going to be m times L squared. So this is my governing ODE. Now look here. This term here, which is, if you get rid of that and put it here, this negative Ka squared theta 1 can go to this side. Also, this mg term can go to this side if you want. And you can keep this positive term Ka squared theta 2 on the other side. Or you can bring all of them to one side. And if you do so, this is going to be your governing ODE. Similarly, by taking moment about this pivot, you're going to get this ODE. Now, if you bring everything to one side and simplify, your equation is going to be written again into matrix format. So you have vector theta double dot times this matrix, which you might call it I or M or whatever you want to call it, plus this matrix, which you might call it K again, times the vector theta, again, is equal to vector 0. And again, we do the exact same thing as last time. We form matrix A, which was M inverse K. We find the eigenvalues of it. We find the eigenvectors of it. And if you do, the first eigenvalue is going to be square root G over L. The first mode shape is going to be 1 to 1. So another way to write this is 1 to 1. The second frequency is going to be this one. And the second mode shape, as you can see, is negative 1. So it's like 1 to negative 1. So these are your mode shapes, and these are your natural frequencies of the system, which you can get using eigenvalues of this matrix and eigenvectors of this matrix. Of course, remember again, when you find the eigenvalues of this matrix, lambdas, you have to take a square root of them to get these omegas, and that's where you see these square root coming from. But the eigenvectors are directly these mode shapes that you can see here. Good. So, and I leave that part of it, that algebra of it, up to you. What I want to explain here is the meaning of these. So what's the meaning of them? The meaning is this. In the first mode shape, if only the first frequency is activated, the angle for both of the pendulas are going to be 1 to 1. What does it mean? I mean, both of them move the same angle, move the same ratio. So both of them move with the same angle. In that case, they act like a single pendulum, basically. And remember, the frequency of a single pendulum is what? Square root G over L. That's exactly what it is. In scenario 2, the angles are in the negative direction of each other. So while this pendulum is moving to the right, this pendulum moves to the left. So you get this kind of scenario. Okay, this one is going to go this way, this one is going to go the other way. And because of that, again, because it's one and negative one, the point in the middle, or if you look at the spring, this point here in the middle of the spring is going to be a node. That is going to be a point that does not move. So in the second mode, the spring is going to be compressed when they come like this, and when they move to the other side, so this goes here, this goes there, then the spring will be stretched. But the point in the middle of it, regardless of the spring being stretched or compressed, this point in the middle will not move. It is going to stay there, and it is going to be called a node. But when they are in oscillating in sync, they move with the same frequency and with the same amplitude all the time. Now, what kind of solution would you get here? If you want to write down the general format of the solution, what kind of solution would you have here? So theta 1 of t is going to be some unknown theta times sine of square root g over L times t plus phi plus another unknown theta times sine of the other frequency times t plus psi. So the other one was g over L plus, let's just copy it from here. So 2ka squared over ml squared. So that's the solution for angle 1. And for solution for angle 2, the same theta goes here, but remember the weight for the first frequency was 1 to 1. And then for this one, with the same frequency again, the weight is going to be 1 to negative 1. So we can change that to a negative. Okay? These are the general format of the solution. And what are the unknowns? The unknowns is this unknown theta 1, unknown theta 2, unknown phi, unknown psi. But remember, you have 4 initial conditions: theta 1 at 0, theta 2 at 0, as well as what? Theta 1 dot at 0 and theta 2 dot at 0. If you know these 4 initial conditions, you can determine those 4 constants, and that is your solution. Again, if your initial condition, let's say you release them from rest, so both of these theta dots are 0, let's say for a moment. If, for instance, you release the first angle at, let's say, 60 degrees, and maybe this one at 45 degrees, the question is, which one of these theta 1 or 2 is going to be bigger? You are right. This vector here is closer to 1, 1 than to negative 1, 1. Because it's closer to that, theta 1 is going to be bigger than theta 2. But if one of the angles I did negative 60 and positive 40, this one is closer now to this. In that case, when you solve, theta 2 is going to be bigger than theta 1. So the second frequency will be dominant because I started the system closer to that second frequency. Actually, you can show something. Let me tell you this before I move on. If I exactly start my initial condition like one of the mode shapes, what does that mean? It means if I exactly start at pi over 3 and pi over 3, So ratio 1 to 1. So I exactly start at this mode shape with the same weight, right? The same ratio. Guess how much theta 2 is going to be? You are right. Brilliant. This is going to be 0. And these guys are going to be 1. In that case, the second frequency will be eliminated. The only frequency I will see in the system will only be the first frequency because I started the system exactly like the first mode shape. Similarly, if I put a negative here and I start it, theta 1 will be 0, theta 2 will not be 0. I would eliminate the first frequency. So I can pick which frequencies to activate and which frequencies to keep as silent just by picking proper initial conditions. When I know my mode shapes, I can pick an initial condition exactly similar to one of them and I can only activate that frequency. The rest of them will be 0. But if it's somewhere between these mode shapes, then all of these weights are going to be non-zero. The closer it is to each one of them, the bigger the weight of that, the smaller the weight of the rest. Okay, so now you start to see the meaning of mode shapes with this example. Finally, I know this video is getting long, but I really want to tell you everything you need to know about free vibrations of multi-DOF systems. Finally, what if you have damping? If there is damping, you need to do some extra thing to find the damped natural frequencies. And it's interesting, if you look at the textbook that I use, it does not address this problem. It just skipped it. All the textbook has solved are the systems without damping. So here I tell you what happens if you add damping to the system. So if I add damping, then the spring forces are like last time. The damper forces are going to be similar, except they have C's and X dots instead of K and X. So if you write the equations for each one of them in the X direction, and you will get these two ODEs. And if you sort it out, then in matrix format, you will get this, where not only you have mx double dot and kx, now you have this extra matrix C times x dot. So this viscous damping term is now added to my equations. So, can I still solve this? Yes. Well, if I assume my solution is an exponential, like any other second order linear ODE with constant coefficients, the solution is going to be an exponential. Remember, this lambda could be a complex number. Last time we assumed I omega n. Remember last time we said this is x times e to the I omega n t. So x here is the same as phi. And this I omega n is the same as lambda. So lambda here is not a real number necessarily. It could be a complex number. Okay? So if I plug that into the solution, x dot is going to be lambda phi times e to the lambda t. And x double dot is going to be lambda squared. So if you plug it in, it is going to be all of this equals 0. Okay? And if you look at this, as opposed to last time, this is not a simple eigenvalue problem. I mean, if this guy was not there, that would exactly be an eigenvalue problem, right? Because it would be the same thing. Remember, m lambda squared equals negative k, correct? Times phi, of course. And now I multiply both sides by m inverse. And guess what? I get a similar thing. Again, I will get this matrix. And here I will get the eigenvalue problems that I had. But this time, because of this C lambda, it's not as simple as that. I cannot just simply multiply both sides by m inverse. I will get an extra term, m inverse C, and that is called a generalized eigenvalue problem. And lambdas are the eigenvalues and phi's are the eigenvectors of it. But instead of solving this, which is not trivial, the best way to handle it is to convert your governing equations into first order ODEs. Like when you want to numerically solve them with ODE 45 in MATLAB, or when you want to do state space control, you pick some dummy variables and convert these 2 second order ODEs into 4 first order ODEs. So the first thing is pick 4 dummy variables. Which dummy variables? It's up to you. The simplest thing you can pick is x1 and x2 and then x1 dot and x2 dot. If you pick these and call it z vector, then you can write the 4 first order ODEs in terms of z. Well, let me show you how. So here I look at the time derivative of this z. So I'm looking at z dot. Well, because z is x vector and x dot vector, and here this x is like x1, x2, and this x dot is like x1 dot, x2 dot. Okay? Then the time derivative of that will be what? Well, the time derivative of x is x dot, as we know, and the time derivative of x dot, which is x double dot vector, is going to be what? Well, all I need is to solve for x double dot from this equation here. How do I solve? I take k to the other side and c to the other side, and then multiply both sides by m inverse. So you will get m inverse c x dot with this negative sign and negative m inverse kx, which is exactly this. Good? Now this, I can write it as some matrix times the original z, which was x and x dot. How? Well, this x dot, I can write it as 0 times x plus I times x dot. So that 0 and I are going to go there. And this one, I can write it as negative k inverse m times x and negative m inverse times c x dot. Therefore, these two will sit there. So now you see I have written my governing ODEs into 4 first order ODEs in this format. That z dot equals some matrix times z. And that matrix here, I call it the A matrix. So now I have written my original ODEs, which were in this format. Okay. I started with this, which led to this one and not easy to solve. I converted that into this, which is much easier to handle with this A matrix. Well, now if I go back and assume an exponential solution again, except for phi, I just call the mode shape for z, I call it z0, or you can call it capital Z or whatever, and e to the lambda t. If I plug it in, z dot is going to be what? Is going to be lambda z naught e to the lambda t. Now this is equal to a times z, and a times z means a z naught e to the lambda t. That is a z naught. Az. And then look what? This e to the lambda t, which is not 0, I can simplify, and I get a z naught equals lambda z naught. And this is a simple eigenvalue problem that we know how to solve. There we go, done. You see, I don't need to solve this anymore. I solved this one, which is very easy to solve, a simple eigenvalue problem. So lambdas, which are the natural frequencies of the system, but not regular, they're damped natural frequencies of the system, are going to be eigenvalues of A, and then Z0, the mode shapes, are going to be what? The eigenvectors of matrix A. So all I need to form is this matrix A, this guy. And look at the eigenvalues of that. That's all I need to do. You see how beautiful it is? Just form the matrix A and go for it. Now here, to show you a demo, I have written a simple MATLAB code, which I'm going to give you a download link. So here I have values for M1, M2, K1 to K3, and C1 to C3 in SI units. I formed the M matrix, I formed the K matrix, I formed the C matrix, just like here. Look, these are exactly these guys. M, C, and K. I form these, and then using those, I form my A matrix here. Remember, this A is a 4 by 4 matrix. So when I say 0, that's not number 0, that's a 2 by 2 matrix of 0. And this identity matrix is also a 2 by 2 identity matrix. Okay? So if I go back, look, when I form A, you see a 0, 2, or 0, 2 by 2, I 2 by 2, then M inverse K and M inverse times a C. So I find the A matrix, then I pass it to the eigenvalue. It gives me the eigenvalues and eigenvectors. Now, eigenvalues, as I said, could be complex numbers. And look, if I run it, actually you'll see that they are actually complex numbers. Let me show you these eigenvalues here. Look, these are my eigenvalues. We only need to look at the diagonals, right? Look, they all have complex portion, because this system has a harmonic response. So all of them are complex. Okay, now how do I find my natural frequencies? Well, if you remember from what we had in the single DOF systems, when I had a damped system, the eigenvalues were what? You're right. The eigenvalues, in this case, lambda, please pay attention. In this case, lambda is not the square of the natural frequencies. In this case, lambda is the eigenvalue of the Z matrix. And that's basically what? If you remember, it's negative zeta omega n plus minus omega n times square root 1 minus zeta squared, right? Times I. Where this guy here, we called it omega d, the damped natural frequency, and this part was that negative exponential, sigma. So if I want my damped natural frequencies, all I need to look is in the imaginary part of these lambdas. If I look at the imaginary part of these lambdas, those are my damped natural frequencies. So look here, I get the diagonals of that matrix, and then I look at their imaginary part. And if you look here, every two of these lambdas are complex conjugate of each other. So this is one of those imaginary parts, 4364, and the other one is what? 22. So this is one of my omega d's, this is one of my omega d's. Look, these are my damped natural frequencies in radians per second. And again, pay attention. In this case, you do not need to take a square root, because we already converted the system into a 4 by 4 or 4 by 1. So there is no square anymore here. My ODs are first order, not second, so I don't need to take any square root. Be careful about that. And since the first and the second are complex conjugate and the third and fourth are complex conjugate, look, when I pick the imaginary parts, I pick number 1 and I pick number 3, the ones that are not conjugate of each other. Otherwise, I get the same number. So these are my omega d's. Then I can find the damping factors for them. Well, how would you find damping factor? Remember, if I have this real part, this is the real part that I have, and I have this part, which is the imaginary part, from these two, can I find zeta? Yes. What I need to do is to square them and add them together. If I do that, you will get zeta squared omega n squared plus omega n squared 1 minus zeta squared. These two negative positives would cancel. You simply get omega n squared. So if I take a square root of that, it will be omega n. So I can find the natural frequencies also if I want. And then what? If I divide this real part by omega n with a negative sign, so negative of the real part divided by this omega n, it's going to be negative of negative zeta omega n over omega n. So you will get zeta. Okay, and that is exactly what you see here I'm doing in this code. Look. So this is zeta. If you want, you can do omega n as well. Okay, this square root here is exactly omega n. So if you want, you can also add that to the code and say compute natural frequencies, right? Compute undamped natural frequencies, because these guys are here. These are the damped natural frequencies. So undamped one, you can call them here omega n, for instance, if you want. And you can later show them as well. So you see here, when I show damped natural frequencies, I can come here and show undamped natural frequencies, and I use omega n. Okay, so I can show those as well. I have omega n, I have zeta, and then for mode shapes, I need to go to the eigenvectors. And again, since I picked 1 and 3 for eigenvalues, for eigenvectors, I also pick 1 and 3, 1 and 3. And then I divide them by their magnitude to normalize it, to make sure one of the elements in it is basically of magnitude 1. And then I show it again. Look, there we go. So these are my damped natural frequencies. Undamped doesn't look right. Well, no, actually it does. These numbers are not the same. Look, this is 43, this is 44, this is 23, 22.3, this is 22.4. The reason is the damping factors are very small in the system. Okay, the damping factors are very small. Why? Because compare the C values to the Ks and Ms, especially to the Ks. These are small dampings. If I go by order of magnitude, you definitely expect bigger zetas. Look now, one of them is even 1. Well, maybe we went too far, so let me make this 60 and let me make this 20. So still one of them is 1. So let's see if I can go below 1. There we go. You see now the damped frequencies and the undamped frequencies are quite a bit different. And these are your damping factors, and these are your mode shapes. One of them is this, the other one is this one. Okay, so hopefully this code will help you. You can play with it. You can see different natural frequencies of the system for mass spring damper and learn from it. I'll give you a download link under video description. I know the video went long, but this was a very critical and important topic. So hopefully you enjoyed it. Thank you.